Welcome to the last day of class. The tyranny of all is near the end. Don't forget, math club this afternoon. If you're interested, we'll talk to you about the Chinese negative theorem, but in the speaker's script, I think it can also be kind of fun. Math in tomorrow will take place from 10 a.m. to 5 p.m. here on part 2 course of this building. Look, it's not just where you go. It's a good day to come by, get ready for your mathing kind of finals coming up. And we will have a separate review session Tuesday in M203 at 5:30.
Okay, there's paper.
Okay, this is the last theorem that we were talking about last time. This is a cool ideal theoretic way to characterize UFDs. R is UFD if and only if every non-zero prime ideal contains a non-zero prime element. Last time we did one implies the easier will play. So let's do 2 implies 1. For this one, we'll suppose 2 holes. Let S be multiply set of R generated times the units. So in other words, a typical element of S so a typical element that's in the set that I say is generated by quantum units is either a unit or it's a unit times a bunch of primes, which again is a bunch of primes. What happens when you take 2 products of primes and multiply them, you get a bigger product of primes. So this is certainly multiple. Everybody okay with that? Our goal this would show that it's a UFD because if this set is all non-zero elements of R, that means everything that's not zero is either a unit or a product of primes. And we already know that products of primes are unique. We keep that last, right? So everybody on board with why this is our goal. Right? So to that end, let's do this. Suppose that X R is a non-zero unit. And X is not a product of primes. Suppose that such an animal exists. Right. So this, of course, this just means that X is not a set X. I claim the ideal generated by X intersect S is empty. And let me justify this point. If not, then there exists R and R such that Rx now certainly what does an element of S look like? Well, it's either a unit or it's a product of primes. It certainly can't be the case that S is a unit, because if S is a unit, if S is a unit, that means that X is a unit as well. And that's a contradiction. So we can't have that. So S must be a product of primes. plus most of the primes there. And what I'm gonna do here, is go by induction here. So notice now, I went through that a little bit quickly. Let me explain this to you. If Rx is just a single prime, notice a single non-zero prime is irreducible. That means one of these two has to be a unit, right? X already we've discussed can't be a unit. And if R is that means that X is essentially prime because it's a unit times X is a unit times prime. So, by induction, we assume that if Rx P1, P2, Pn, then X is a prime. Now suppose now assume that Rx is probably plus one primes. Show this can't pass. Notice that P and now we've got it because this implies Pn plus one minus R. Well, Pn plus one is prime and has to divide one of x2 from your Euclidean basis. And this means R is R prime Pn plus one, or R equals, or I'm sorry, X equals Pn plus one X prime. So in the first case, this gives R prime Pn plus one X equals P1 Pn Pn plus one. Canceling the Pn plus ones. And so X is a plus by induction. Right. For my inductive step, if I ever have something times X product, I think of the product primes. Step two, if the second thing happens, then I have R Pn plus one X prime. And so this means that R X prime is P1 of Pn. And so what I have is by induction again, X prime is a product. Right. By induction, I apply my induction step to X prime. X prime is a product of some number of primes, which I'll call Q. And now I can lift this back up to the previous, because remember, this means that Pn plus one X prime, which is X, is equal to Q1 QL plus one is a value. So in either case, I satisfied, well, my inductive argument is working. So. There we go. We've got the big piece of close beginning. Okay, so the ideal generated by X intersect that set that's generated by units and primes is empty. So what does that mean I can do to X? What happens when I have an ideal that this small quantitative set?
You expand it to
Right. Expand X to prime. Each sub X containing X. Such that and what's the problem?
Actually, it's kind of maximal with respect to the property that,
It's maximal with respect to the property that misses S, right?
so P of X equals X.
No, not necessarily. A piece of X is an ideal that contains X. But what does property do to tell us? Right? What is our assumption at the beginning? What does property do say? That every, by the way, since X is not zero, this is a non-zero prime ideal. So what must happen? It must, by assumption here, our second condition says every non-zero prime ideal contains a non-zero prime element. There it says C X a non-zero prime element. But C is an S. Because S contains all primes. So there exists, as you know, there doesn't exist a non-zero non-unit outside of S. So R minus zero plus S and R. Because every non-zero element is product is either a unit or product of primes. Okay, any questions on that? By the way, this is a great theorem. Your UFD, if and only if every non-zero prime ideal contains a non-zero prime element. Fields vacuously UFDs. Here is a big theorem. And the previous theorem, if you look at other textbooks, they'll do this a different way. It's much more long and you can things about ascending chains and whatnot. This is a quicker way to do it. Let R be we have 1 implies 2 implies 3 and none are reversible in general. One R is Euclidean. R is Euclidean domain. 2 R is EID. 3 R is no. So any domain that has a Euclidean algorithm is automatically a principal ideal domain. And anything that is a principal ideal domain is automatically a UFD. By the way, this is just kind of of interest for some of you like the logic kind of stuff. The proof from here to here is fairly easy. We'll go through it. The proof from here to here cannot be done without the action of choice. In fact, it's been proven it can't be done without the action of choice. It'll be easy in the theory, in the proof that I'm going to give you. We've already done the action of choice in the previous, my characterization of UFD, where every non-zero prime deals with a non-zero element. That's where choice came in. Also with, yeah, and I'll give you some examples to show the reversible. 1 implies 2. Suppose R is you with Euclidean function phi. Remember, this is from R, non-zero elements for R, the natural numbers equal 0. Let I and R be a natural. Anybody know how? Of course, my claim is this is going to be a principal ideal domain, right? So if this is correct, then I have to have the principal generator. Any ideas how to find it? Somehow I'm going to need to use this thing to find it. Let's let take your Euclidean function and measure everything in the ideal that's not 0, because 0 is, of course, undefined in this function. Yes,
That's true. So it's a property.
actually doesn't matter. I do want this ideal to be non-zero, but of course, 0 ideal is principal, right? So I don't think we're worried about that. Any ideas on candidate generator? Why? Let me point out that this is barfing out all this information. I go through and I use phi on every non-zero element, and it gives me what? A natural number. So if I gather this all in a pile, this is a subset of the natural number Q0, right? I agree. And any subset of the natural number Q0 has small stuff. And of course, this is a non-empty subset, okay, because I is not the 0 ideal. Oh, yes, too bad thing. This is not empty, it's a subset of n0. So m as n1. Let C be this minimal. Well, let C be a element with a minimal norm. I don't claim this is unique, just pick one of the many of them. I claim this containment is clear because C is contained in I. So the ideal generated by C must be contained in I. The other way is more interesting. Or this contained, now suppose. What am I going to do to alpha? I'm going to apply the Euclidean alpha, or this facsimile Euclidean alpha. There exists Q R in R such that alpha is equal to QZ plus R. What? What conditions do I have on R? Right, that's the whole point of the algorithm is you get something smaller as a remainder which you divide by. Notice that alpha is in I and Z is in I, so alpha minus QZ, which is R, is in. So because Z was supposed to be the element of I that, or an element of I that had the minimum Euclidean norm. Therefore, R equals 0 and alpha QZ is in the identity. And R. Any questions on that? Okay, last indication. I'll show the PIDs and UFD. So.
Well, another circuit bigger. They have like 2 more.
Suppose R is principal given, right? If R is equal, then that. Because any field is a UFD vacuous. If R is not a field, then R has a nonzero field. Suppose P is any nonzero prime ideal. Then R. Okay. Since R is a PID, what's this mean? It means P is generated by a single element, right? And we actually have a theorem from last time. Since X generates a prime ideal P, what can we say about the status of X as an element? Since any prime P contains a non-zero prime element, or it doesn't appear that we use the accident choice there, but we did because this characterization here, use the axiom of choice for us. Okay, any questions on that? Let me give you examples. Uh, um, Cx is a UFD. This follows from the theorem that I'm going to give you in a moment. It turns out that if you have any unique factorization domains, polynomial domains, unique factorization, but not yeah, it's in a sense is too big to be a kid. The ideal derivative 2 in x is not reversible. Let me give you an intuitive proof, really kind of a talk through. What's the degree of 2? It's a polynomial. 0, right? And the degree of x is 1. If there were a principal generator to this ideal, that principal generator would have to divide both 2 and x, right? Well, that would mean that it would have to be of degree 0 because you're not dividing 2 with anything of degree higher than 0, right? So in other words, any principal generator of this must be a constant. Now, the only possible divisors of 2 are plus or minus 2 and plus or minus 1. Notice that 2 doesn't divide x because 1/2 x is not x, right? So you're only essentially left with 1, right? But this, it's easy to show as a proper ideal because this is the ideal of all, these are all polynomials of z where the constant term z. And 1 is odd, so it can't be a constant term. So this is an example of the UFD, but this idea is on the principle. Finding examples of principal ideal domains that aren't Euclidean is trickier. And in fact, there are even papers coming out fairly recently where people discover or explore various places where they can do that. So it's actually, some people are still interested in this thing. Here is kind of a classical example, and the proof will take too much time for me to do it, but if you're interested, I'll have to discuss it with you at a future time. It's a classic number theory. Take the smallest ring that contains z and the complex number 1 plus the square root of -19/2. As it turns out, you may wonder, it's kind of hard to prove. How do you know that there's not some Euclidean algorithm on this? But there's actually a technique for showing that such a thing can't exist in this ring. It is a principal ideal domain, but it is not Euclidean. And that would require some out of class stuff if you wanted to discuss why that's true. Give you some rhythm here, and then a couple more theorems, and I'll kind of discuss why that's true. See. If P or prime so if you have an element of R that is prime, then it's also prime in the polynomial, right? This may not be too surprising, but let me just kind of put together the proof. And this is a nice application of some of our other theorems. if you look at R, right, I did learn about R. When you take any ring and mod out, any ring one mod out by a prime ideal, you get what I remember? Right, integral domain. So we're going to use this polynomial result. And this, we look at Rx mod PRX. This is isomorphic to on my P X from the earlier result, which is a domain. Because R mod P is a domain, so in a polynomial ring over a domain is a domain. I've already shown that. So PRX and RX. So P prime. Because P is what generates that prime line. So I am going to give you three theorems that I'm going to discuss. One of them is proved in the notes, which I might come back and go over this a little bit, but I want to hit you up with these kind of big theorems before we get out. And here's one that I alluded to just a moment ago. And this is a big one. If R is a UFD, so it's polynomial. This one is huge, and it's what makes, again, an important aspect of ring theory why it's important. If you have unique factorization for coefficients, then that unique factorization persists when you move up to polynomials. From this follows right, by induction, because if R is UFD, then this is. Now this is a UFD, so you add another polynomial variable and so forth and so on. And the corollary has a corollary. You can have a polynomial ring and an uncountable number of variables and it's still a vector. And this is really a corollary of this, because if you have any element in here, even though there's only uncountably many variables, you only see finitely many of them at a time in any particular element. So if I just give you a polynomial ring, you can only use finitely many of the variables to represent that particular one that you picked out. And that particular one that you picked out sits in one of these, and so has unique factorization of primes. Yes?
You can only pick finitely many because this is our, like.
By definition, the definition of a polynomial ring and infinitely many, it's always a finite sum. And your monomials can only involve finitely many of the variables. So no matter what, you're going to be in that, even though the ring itself has as many variables, x1, x2, however many you want, any particular element you pick out has to sit in a finite.
Because it's not our power.
Well, the power series, this theorem isn't even true for power series. It is possible to have unique factorization domain whose power series is not. And that behavior is still to this day not completely, I would say, understood. Here is another theorem. This was kind of this is called Eisenstein's theorem. This is Eisenstein's irreducibility project. This is really a groovy way to find irreducible polynomials. So here's the more general statement. Let R be the domain, E integral domain, and f of x and this is a polynomial with coefficients in I'll assume that these are all coefficients R, and I'll assume that I haven't done anything stupid, like have a leading coefficient sigma. That would be rather silly of me. If so, suppose that R has a prime element that's not zero, and suppose that it doesn't divide AN. So I don't want it to divide the leading coefficient. But it divides all the other coefficients. And I've got one more caveat. So here's my rule. P doesn't divide the leading coefficient, but it divides all the rest of them. And P squared doesn't divide the last one. So A0 only harbors one factor of P. It can't be more than one factor of P. Then the only possible proper factors of that is easy. That is, the only thing that you could ever hope to do is pull out constants. You can't break that down into smaller degree polynomials. You're stuck at that degree. Additionally, if R is UFD, if R is a UFD, the function okay, then f of x is this. Okay, let me give you a couple of examples of this. And let me kind of explain what this means here. Let's look at this polynomial right here. Does anybody see a prime that satisfies the criteria we have here for further Eisenstein? Well, I guess it can't be three, can it? Because three divides the leading coefficient. That's right, two. Notice two words, because two doesn't divide leading coefficient, but two does divide, this, and two squared, it's not divided. So this is irreducible. This is irreducible over both ZX and pairs, because the only thing that you can pull out are constants, right? And the only constant you have a pair of in will pull out is three, right? But three doesn't divide 14. Let me change my example just a little bit. Is also I call this E Eisenstein, two Eisenstein, and is irreducible in QX. But this time, not in ZX. Somebody clear this up for me. How come it's not irreducible in CX? Well, three, can't you? Do I agree with that? Well, why is this? Dang it. Certainly, this is a factorization in CX. This polynomial times this polynomial, right? Why? Why is it irreducible in QX? What's true about this in Q that's not true about it in Z?
It's part of the Z.
Well, and what is it in Q? It's a unit. That's why this thing is irreducible, because when I factor the display in QX, this is a unit, right? In Z, it's not a unit. And so that's the technical catch there about at the end of Eisenstein. Any questions on it? Let me show you kind of a trick that's kind of cool. If we look at this polynomial here, notice 2 doesn't divide the leading coefficient, this is mine, but it divides every other coefficient, and it only divides the constant term once, because you divide 2 into 1 of 2. This is 2 Eisenstein. Irreducible in CX and QXs. Right, and that's, I mean, nobody wants to test that crap, right? I mean, if you use something old-fashioned, y'all remember the rational root test you may have had earlier. You could go through the possible rational roots, and there's a number of them. Nobody wants to test that. And even if it doesn't have rational roots, that doesn't mean this doesn't split into a irreducible quadratic times an irreducible cubic. But it doesn't. Eisenstein tells you that. Try to prove Eisenstein yourself. It's actually not difficult. When you start to write it down and set it up, the business about p squared not dividing the constant term becomes pretty clear as to how you're avoiding it to be able to break down. Let me give you another example. you can use Eisenstein's on this as well. But how, you might say, you might say it loudly, because there are no problems that divide any of these. Yes.
When you say like two Eisenstein versus reversible, like what is two Eisenstein? Like what's the difference?
That means that the prime two works for Eisenstein's criterion.
Okay.
Where it doesn't divide the leading coefficient, it divides all the others and squared it by the constant. Check out this. Place x by x plus 1. This gives me x4 plus 4x plus 6x squared plus 4x plus 1 plus x cubed plus 3x squared plus 3x plus 1 plus x squared plus 2x plus 1 plus x plus 1 plus 1, which equals x to the 4, 4 and 1, 5, 10, so this is 5 Eisenstein. So the point is that sometimes if you're clever, you might be able to take something that's not Eisenstein and do a little prestidigitation and come up with something else. Since this thing is irreducible, you can back substitute and prove that the original one has to be irreducible. Okay. Any questions? Okay. I have one last theorem for you, and then I will set you along your merry way. And these are famous ones. You might think about how to prove them. The techniques are actually different. Let's take this. Suppose an article theory. Remember what that means? It means that every ideal is finitely generated. Then number one, Rx. And this is called Hilbert Basis Theorem. A very famous theorem. This is basically, this is, one can argue that this is basically something behind the reason why the theory rings are important. The theory rings, all the ideals are finitely generated. And that means that you can get your hands on being able to compute things, because it's harder to compute things if you've got infinite generators. If you only got finite many, you get your hands on it. And what makes this theorem striking is if every ideal in R is finitely generated, this is also true for the polynomial ring. So that means that if you can do nice computations here, because the ideals are finitely generated, then this nice property persists here. So that's why polynomial rings, another reason why polynomial rings are important. And the same is true for mappings. The techniques for showing these are actually quite different, very different, as a matter of fact, or at least the standard ones. So you might put that in your tool bag because it's useful and think about why it's true. And that's that. We've got the review. So don't forget the math in tomorrow. Don't forget the review session on Tuesday. And if you got any questions, I will have I will have my usual office hours, including the class time. So I'll be there early until afternoon on Mondays, and Wednesday for sure. Tuesday night, I just get a hold of these meeting things. Once my student, always my student, but if you need help to you in the future, let me know. Kick some butt on the phone and that's what it's great.